want to find the general solution to the second order differential equation 2y double prime minus y prime minus y equals 0. So what we want to do from the previous problem, from the introductory example here, we saw that a general solution is going to be of the form a c1 e to the x plus c2 e to the 2x, and the particular solutions are going to be of the form y equals e to the rx. This is what a particular solution is going to look like. And if we take its derivatives, we get y prime equals r e to the rx, and y double prime equals r squared e to the rx. And we can say, okay, if a solution is going to look like e to the rx, then we can take its derivatives along with the original function and plug it into the differential equation, 2y double prime minus y prime minus y equals 0. And when we plug these in, we get 2r squared e to the rx minus r e to the rx minus e to the rx equals 0. And our goal here is to find the value of r that is going to work for this specific differential equation. And I'm going to write this specifically over here. The linearly independent solutions we want to find to start are of the form y equals e to the rx. All right. So that's what we're doing here. So we take its derivatives, plug it into the differential equation. Going back here, 2r squared e to the rx minus r e to the rx minus e to the rx. We can factor out e to the rx from this whole thing. And we're left with 2r squared minus r minus 1 equals 0. Now, e to the rx is always positive. No matter what r and x are, that will always be a positive value. So we can divide it out and say that the only solutions to this equation are going to be from 2r squared minus r minus 1 equals 0. From this, we can, in this case, factor. We would use the quadratic formula if we couldn't, but this will factor as 2r plus 1, I think, and then r minus 1. Let's just double check. Negative 2r plus a single r will be a negative r. So that works. That equals 0. So r equals negative 1/2. We'll say that's r1, or r2 equals 1. So we have two different r values that work here. This means that our linearly independent solutions are y1 equals e to the negative 1/2 x, and y2 equals e to the x. From this, we can say what our general solution is. It's the linear combinations of these particular solutions. So that's going to be y sub g of x equals c1 e to the negative 1/2 x plus c2 e to the x. And we're done. That is the general solution to this second order differential equation. I want to say one other thing on this before we do another example. This right here, the 2r squared minus r minus 1 equals 0. This is called the characteristic equation. And it's called the characteristic equation because it's characteristic of all of these homogeneous second order differential equations. It's characteristic that this will always occur. So we can, in following problems, always jump to the characteristic equation in order to find our r values straight away and quickly jump to our general solution. So we'll state this generally now. Given a homogeneous second order differential equation of the form a y double prime plus by prime plus cy equals 0. The characteristic equation is ar squared plus br plus c equals 0. And we can say further that the general solution to the differential equation will be y sub g of, I'm going to use t here, t or x or whatever the input variable you want is, y sub g of t equals c1 e to the r1t plus c2 e to the r2t when r1 and r2 are distinct solutions to the characteristic equation. All right, one last thing to add real quick is something that we're going to address later, is that if the characteristic equation doesn't have distinct roots, how would we address that scenario? So we're going to look at that in a following problem, not in this video right now, but just keep in mind that that would be a special case that needs to be looked at in its own right. All right, thank you much, and we'll see you on the next problem.